So this is number 52 from chapter 13, and it's just a general, almost like theory kind of question. And it's saying that we have a reaction, say it's AB going to A plus B, right? Now, this is just, and it's trying to figure out, we're going to have to figure out what these different values are. So A is asking us, if we say, knowing that we plot 1 versus concentration, 1 over concentration versus time. So let's just make a little sketch of that. 1 over concentration of AB over versus time gives a slope of negative 0.055 meters seconds. Now, we can make that per meter seconds, right? Yeah. I missed that? Okay. Now, roughly, that is a negative slope, right? That's all we need to be in mind with. It's a negative slope. So what does this sketch represent? It represents a very second order kind of reaction. So that is going to be what we need to be thinking about. So for the K at this temperature, our K is simply, what is the slope of a second order? We know that it is second order. So second order reaction, right? Now in a second order reaction, we know the slope is equal to negative K. So if the slope, negative K is the slope. So if we have negative 0.055 is the slope, so then we know the K is going to be just the positive version, right? That's our positive version. Now that is our simple and easy enough, the slope. Now we're going to keep the same units, by the way, per meters, molarity second, sorry. I don't know why I said meters. Okay, now B is the rate law. The rate law for a second order reaction, which you already determined, can be in the general term, right? Rate equals K reactant squared. So the rate is going to equal K times the constant, right, squared, since it's a second order reaction. We're going to have K times AB squared. That's going to be our second order reaction. Now, this one's also looking for the half-life when the initial concentration is 0.55 molar. Now, remember, in a first order reaction, you don't need to know the initial concentration because the half-life will never change. But in a second order and a zero order reaction, half-life is very much dependent on the original concentration, initial concentration. So in this one, we have our formula, right, for a T half-life. And that is T half-life is going to be equal 1 over K times the concentration of AB at time 0, the original concentration, initial concentration. So we can just plug in the values, and we're going to get 1 over 0.55 times initial concentration of 0.55 molar. And when we solve it out, that is roughly 33 seconds. I remember the units of K are molar per molar seconds, right? So, well, that just made it more complicated. But it is per molar times seconds. So we're going to cancel out molars, and that's how we're going to get per seconds. So this one is just like that. And I know part D talks about finding the concentration of AB, and that you're going to plug into the second integrated rate law for a second order reaction. But for these three, what I wanted to show you was the half-life especially. You are dependent on the original concentration. And from the negative slope, you can deduce that it is a second order reaction.